Lesson 7-3, both parts A and B, days A and B, are going to be dealing with the technique of integrating a product. One of the fallacies, one of the falsehoods about integrals, you can add them, you can subtract them, you cannot multiply. And so when you have a product and u substitution didn't work, okay, you should still always try u substitution first, because a lot of times it's set up so u substitution will work. But what I'm going to show you today is another strategy. Well, what do you do if u substitution doesn't work? If the u you chose, and it's not like it was a bad u, it was a good u, but what if things don't reduce the way they're supposed to or the way you would like? Because in u substitution, you really just want a whole boom, 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 stuff all reduces, and you're left with this really nice, simple integral to do. So what happens if you don't? So you need a new technique, and this is called parts substitution, or integration by parts. So we've done u substitution, and so if, that's really all I have to say to you sometimes. You're like, I'm stuck, and I'll go, try u substitution. Or now I'm going to teach you a new technique. I'm stuck. Try part substitution. And we'll do try trig substitution and there's all these different methods. So parts. Okay, well, what parts are we talking about? Well, let's go back to how we did the derivative of a product. And then we'll do how to do the antiderivative. So the derivative of the product was the product rule, aka and so if you had a u times a v, and you wanted to find the derivative of that, you couldn't just do the derivatives and multiply them together. You needed that special rule. And the rule was start with v, and then have du, or u prime, if you're writing it with Newton. And then add to it u, and then the v prime. That was the derivative of a product. So now we go to the antiderivative. Right, it also uses parts. Now look at the derivative of a product. How many distinct parts are there? There are 4, actually. Okay, you start with 2, but when you do it, you end up with 4 pieces. You end up with u itself and a du somewhere. You end up with v itself and a dv somewhere. Those are called the 4 parts of it. And we need to rearrange those 4 parts so that we can do the antiderivative. And we're not going to be using addition. We'll be using subtraction. Okay? All right, so here's how it goes. The antiderivative of u v okay, and the parts get rearranged this way. V times u, not du, minus the integral of v du. Okay, v times u times the integral of v du. Let me put my parentheses differently so that makes a little bit more sense. Should be, there we go. All right, that's the technical way to write it. Let me show you. It's a little easier to show you in an example. And we've got a nice way of organizing it so that it just lines up really nicely for us. Okay, let's try the following product. X cos x dx. Okay, that is a product. U substitution will not work on this product because what would you need to be in there somewhere to reduce away at some point? That's how you say it, Julia. You'd need a sign there somewhere. If you were going to use U substitution, there'd have to be a cosine and a sine so that one reduced the other when you did the derivative, and there isn't. So then this is going to lead to parts. All right, you want to kind of organize yourself this way. Make like a plus sign. Okay, in that plus sign, you want to organize the pieces this way. You want to put your U piece here, and your du piece beneath it. And you'll want to put your dv piece here and your v piece beneath it. Okay, so the diagonals are the differentials are diagonal from each other, and the regular sections are diagonal from each other. That would be how you kind of want to line it up. Okay, then you want to decide what goes where. All right, and there is this awesome little acronym, I think. Okay, we use loves using acronyms in math. Like, remember when you used PEMDAS way back in the day? Right, and then you probably learned an acronym for memorizing the planets, right? All these memory tricks. Okay, so I've got a memory thing for you today. It's a nonsensical word. PEMDAS doesn't make sense unless you know what the letters stand for. And it's the same thing is true here. Okay, L-I-P-E-T, lipid. What this does is it gives you a hierarchy in order. You have to pick your U first, and you're going to pick your U in the following order. So this is your U choice priority list. Ooh. L, logarithm. If one of the parts of, if there's a logarithm present anywhere, that is your top choice for your U. I, inverse trig. I doesn't stand for irrational. You wouldn't have irrational. I, inverse trig. If there is an inverse trig piece, if you didn't have logarithm and you had inverse trig, that would be your second choice. P, polynomial. Okay, if you didn't have one of the first two, okay, polynomial could be linear, it could be quadratic, it could be cubic, any of those. Okay, E, what do you think E stands for? Yes, exponential. That would be your fourth choice. T, there's only really one other category of function we haven't dealt with, trig. Okay, that would be your absolute last choice. All right, so looking at what we have, we've got x, we have cos x. Okay, according to the Lippitt test, right now we have a linear piece and we have a trig piece. So linear falls into the category of polynomial. So our U, according to the Lippitt test, yes ma'am?
When you say polynomial, would it also be the same if you had something like x squared plus x times cosine x? As in a literal polynomial instead of just a part of it?
Sure. Yeah, that's still a polynomial. Yep. Yeah, polynomial can be made up of individual pieces too. Yeah. All right, so according to the Lippitt test, we've got a P. A polynomial beats a trig. Okay, it's like a trump card. And so we're going to set this up. So our setup for this one is to put our x in the position of U. That means everything else The trig part that was left and the differential goes in the dv section. So you split up your two pieces that way. The u choice is the paramount thing. That is the most important. All right, what goes in here is the derivative. So the derivative of x is what? And don't say 1. It's dx. Okay, I should say the differential, not the derivative, the differential. On the other side, change color, goes the antiderivative. Okay, what is the antiderivative of cosine x? Sine x. Don't worry about your plus c, we'll add that at the end. So now we have the pieces. The u and the v are now diagonal from each other, x and sine x. And then the differentials are also diagonal from each other. The answer to this problem goes in the order that I gave you back up here. What comes first is v times u, or it could be u times v. Those are the two diagonal pieces. So sometimes we'll like circle them. Okay, those two. So those go first. X sine x, whichever order makes more sense to write them in. Then minus. And then the integral again. And then this time, let's look back at how it goes. It's the v part combined with the du part, which are those two pieces next to each other. So we get sine x dx. What should happen is that integral piece should be easy to integrate. And so my answer continues, and this would be x sine x minus the integral of sine x, which is negative cosine of x, plus c. And so our final answer, when we have a double negative, x sine x plus cos x plus the constant c. Yes, ma'am?
If you end up with a u of x squared, you'll end up with something like sine x times 2x times dx. Would that require you to do this all over again?
It would, and we're going to do that.
So the reason why you don't have polynomials as your first choice is for every power you're going to have to iterate over. Do you use different variables for that?
Yes.
Okay.
Why isn't the plus c minus?
Oh, it doesn't matter. C is a constant either way, so it doesn't matter. We usually typically just write plus c, but if I multiply a constant by a negative number, I still have a constant, and so we can write just plus c. That's fine. I wouldn't mark you wrong if you wrote minus c, though. That would be fine. It's just a constant either way, and that's the answer. How would you check your work, by the way? What do you mean? Derive what? Derive your answer? And what should you end up with? The original question, which was x sine x, right? Or x cos x, yeah. So to check it, you just take the derivative back again. Okay, but this is the antiderivative of x cos x. X sine x plus cos x plus c. Okay, just going to practice this several times till we feel like we're getting the hang of it. So now you've seen it once, and we'll just keep doing it. Okay, so our second integral we're going to do, this time has bounds on it. This will be x e to the negative x dx. And you want to apply the LIPET priority, the Lipit test, to this. All right, first, the most crucial part is what you choose as your u part. Okay, so according to the hierarchy of Lippitt, what should we choose? The x again, because x is still a linear piece, which is part of a polynomial. E to the negative x is an exponential. It comes later in the priority list. So that means x is chosen as your u, and everything else goes here. Then you want to do the differential going this way, and you want to do the anti going that way. Okay, so the differential on x is dx. The antiderivative of e to the negative x is e to the negative x. So some of you missed this on your quiz, so let's review. E to the negative x divided by -1 and divided by the natural log of e. So to clean that all up, we don't necessarily need the -1 and the natural log of e written there. So I think a cleaner way to write that would be to get rid of those pieces and then just put a negative in front of your e to the negative x. All right, so our answer, we'll start out with the diagonal pieces joined together. So I think the best order to write that in would be the negative in front of x e to the negative x. So I have x times e to the negative x minus the integral. And now I combine the bottom two pieces. So I'll have negative e to the negative x dx. Now I've got a double negative right away, so I can change that to positive. So that'll give me negative x e to the negative x plus the antiderivative of e to the negative x, which again is e to the negative x divided by -1 in the natural log of e plus c. So once again, I'll clean up that antiderivative, and I don't need that natural log of e, and I'll have negative here. Okay, now I did say these were going to have bounds. You don't have to worry about the bounds till you're done, so I'm going to go back and tell you what the bounds were. -1 to 3. So when you're finished, then you put your bracket around and go -1 to 3. And then we'll evaluate that just like we were earlier. So I'll have -3 e to the -3 minus e to the -3 plus c minus parentheses 1 e to the first minus e to the first plus c. So I can see that my plus c's are gone, but so is my e to the first minus e to the first in the second parenthesis. Those cancel each other out as well. So I've got -3 over e cubed is a better way to write that. Minus 1 over e cubed. And since they have a common denominator of e cubed, I can combine these as -4 over e cubed. Okay, any questions so far? All right, let's look at something. I've got 3 more examples I'd like to get through with you. Each one shows something different and unique that we hadn't seen before. Okay, our next example. 2x times the inverse sine of 3x squared dx. Keep taking. All right, our U choice is crucial here. All right, so I'm just going to wait for a suggestion from you guys. Okay, so we're going to use, this time, we have a polynomial combined with an inverse trig. The inverse trig beats out the polynomial, so we'll have sine inverse of 3x squared, which means everything else that wasn't chosen, which is the 2x and the dx, okay, now we're ready to do our differential here. So we have to make sure we haven't forgotten how to do inverse sine. Okay, it's going to be 1 over a square root. The square root that you're doing 1 over is 1 over 1 minus the actual value, which was 3x squared squared. Also times the chain rule. A couple of you got caught by that on your quiz this last time, so we still do have the chain rule. The chain rule applies to 3x squared, so that would give me the chain rule of 6x dx. On the other side, I need to do the antiderivative, so at least this one's pretty simple, and we get x squared. Now comes the combination of the two, and you might be looking at that and going, oh my stars, that just looks horrible, but trust me, it's going to work out really nicely for us. All right, so first we line those two up. So our answer starts with x squared inverse sine of 3x squared. That one's done. Minus the combined integral of the whole next piece. So now I need to combine these two parts together. So when I do that, what will be in my numerator? 6x cubed over 1 minus 9x to the 4th, and then a dx. Now, Holiday was kind of asking a question sort of like this, like, well, what happens now? Okay, now we've had two integrals that were pretty easy for us to do. They just integrated simply. This one will integrate for us, but we need to use another technique to integrate this one. So we go back to a regular old substitution for this. Now I wouldn't recommend using a u substitution because we've already used the letter u. So choose a different letter, A, B, whatever. Okay, so we're going to do another substitution right now. It's like pressing pause on our problem so that we can do a substitution. What do you think we should choose? I'm going to choose A as my substitutionary variable. What should I assign A to B? That sounded funny, A to B. What should I assign A as? Yep. Okay, what is inside of the radical? 1 minus 9x to the 4th. I choose that because dA dx will then be negative 36 x to the 3rd, which looks good to me because I have that 6x cubed in there. And so then I rearrange my terms. So that leads me to have dx being dA over negative 36x cubed. So it's almost like I'm working on a problem within a problem. So I'm just going to kind of pause that right there. This is how I want to have that look. So this will be now for me the integral of 6x cubed times what I chose for A to the negative 1/2 And then what I'm substituting in, which will be dA over negative 36x cubed. So all in all, my x cubes reduce, and I can pull out from this a negative 1/6 as a constant in front of a to the negative 1/2 dA. Now this is something I can integrate. So that will give me negative 1/6 times the integral of a to the positive half, raise my power up, multiply by the reciprocal of my new power, add a plus c. So clean all that up. That'll be 1/3 negative times a to the half plus c. In other words, negative 1/3 times the square root of what I originally chose as 1 minus 9x to the 4th plus c. Now I had pressed pause. So now I need to press unpause. What is immediately before the work I just started doing? Like immediately before. What is right in front of? So I just started the work. I just started this whole work right here. What's preceding that right in the front? A negative. So that negative is going to affect, so I'm going to have negative parentheses, negative 1/3 square root 1 minus 9x to the 4th plus c. And in front of that I had the x squared sine inverse 3x squared. So my overall answer when I distribute the negative is x squared sine inverse 3x squared plus 1/3 of the square root of 1 minus 9x to the 4th, and I still have plus c, because even though I'm distributing a negative, it's still a positive value. Okay, any questions so far? So we hadn't seen that yet. So each time now we've seen something different. First we started with seeing a trig choice compared with polynomial. Then we saw a polynomial with an exponential. Now we saw a polynomial combined with an inverse that required an additional a substitution. Okay, so a couple more things I want you to see. All right, let's try x squared e to the x dx. And we apply the LIPET hierarchy. Polynomial beats exponential. So x squared is our choice. And then everything else, e to the x dx, is left. We do the differential, 2x dx. And the antiderivative, e to the x. So everything looks pretty good so far. So my answer starts with the pairing of the diagonals, x squared paired with e to the x, minus the antiderivative of the combination of the new parts I created. So this would be 2x e to the x with a dx on the end. This needs its own parts integration because I still have a polynomial with an exponential. All right, so again, this is where you press pause, and I'm going to set up another integration by parts. Polynomial still beats exponential. 2x, and then everything else, e to the x dx. So my derivative is 2. dx, not just 2, but 2 dx, my antiderivative e to the x again. So this part has its own answer. The answer to this one will be 2x e to the x minus the integral of 2 e to the x dx. Now thankfully this has its own antiderivative. I don't need another integration by parts. So I have 2x e to the x minus 2 e to the x plus c. But keep in mind where we pressed pause. We pressed pause right in here. And so preceding all of that is the negative that we had from before. So we press unpause and we bring the negative back in. So x squared e to the x, distribute the negative, so minus 2x e to the x, distribute the negative again, plus 2 e to the x, and then plus c. And that is my final answer. Again, if I wanted to check my work on that, the derivative of that again, I should end up with what I started. By the way, the one we just did, that combination of the polynomial and an exponential, that exponential part, we call that cyclic. Okay, the exponential part, because it just keeps being its own derivative and antiderivative over and over and over again. Okay, so you have a polynomial paired with a cyclic. When that happens, you end up having to do the process a couple times. So then that leads us to our final example of e to the x cos x. So now we're at the very last of our limit. Like these are the bottom two, an exponential and a trig. Okay, these are the lowest priority because they're both cyclic. E to the x is cyclic. It has a cycle that repeats every single time. Cosine is cyclic. It just takes how many times for it to repeat itself? 4. Okay, but these are just going to almost be trapped within each other. So let me show you. It still works, but let me show you how that's going to go. Okay, exponential still beats trig. Okay, so e to the x would be your u choice. Cos x dx would be what was left. And so our differential would be e to the x dx. Our antiderivative piece is sine of x. Okay, so here's the original question. E to the x cos x dx equals, okay, we combine the diagonals. I have e to the x sine x. I subtract the integral, which would be e to the x sine x dx. I've got an exponential and a trig again. Okay, all right. Do it again. You choose the exponential over the trig. The differential, e to the x dx. The antiderivative this time, negative cos x. So we'll work on that. The diagonals are going to be negative e to the x cos x minus the integral of e to the x negative cos x. That'll become a plus. An exponential and a trig. Okay, that's like, do you do it again? There's no point in doing it again. Every time you do it again, you're going to end up with the same exponential and trig. Okay, however, what's in front of what I just pressed pause, right? What's in front of it? Let me draw that line again through. I pressed pause here. So So what do I need to do with that negative? I need to distribute it. Okay, so let's see what we've got. I'm going to start the whole thing. I started with e to the x cos x dx. My first integration by parts got me e to the x sine x. Now I have a negative affecting what comes next, so that will be plus e to the x cos x. And then my minus, and then I have e to the x cos x dx. And I forgot my plus c the first time. Okay. What do you notice about the integral we started with and the integral that we're up to so far? It's exactly the same, right? The integral I started with, e to the x cos x, is exactly the same as the integral that I'm up to. I've done it twice, and I'm up to that. Those are called like terms, and you can combine them. And so add e to the x cos x to this side, and add it to the other side. And so this one completely cancels out. And what you're left with is 2 e to the x cos x dx being equal to e to the x sine x plus e to the x cos x plus c. So how do you solve for the original integral? Divide everything by 2. And so the answer is the whole thing over 2. Now if I divide you can write it that way, or you can leave your plus c separate because dividing a constant by 2 is still going to be a constant, so you could write it like that either way. That will always happen. When you have a combination of two cyclics, so an ET, an exponential, and a trig, it will always happen. It takes 2 iterations for you to end up with what you started with, and then combine the like terms to be able to solve. So you're going to have that show up in your homework too. Okay, but it takes twice. So most of these, we've seen it where you had to do integration by parts twice, and then you got to a point where it was something that you could integrate. Okay, any last questions on that?